sometimes wander around and start moving your hands, and now you don't hear it anymore when you put it too low. So somewhere around here, it's the optimum.
Okay. And is this mic live too, or is it?
Hyvää iltaa. Good evening, everyone. Let's have everyone seated. Welcome to the Museum of Finnish Architecture. My name is Reetta Heiskanen and I work here as an interim director. We are very happy to have a new series of woodworks that we have produced in cooperation with the Ministry of Environment as well as Aalto University. This evening we are going to have lectures in 2 parts, as we do in all of these 6 lecture series. So in total, in woodworks, we will provide 12 international perspectives. Let me give the floor to our curator, Professor Pekka Heikkinen, who can introduce you the subject as well as the speakers. You're warmly welcome.
Okay, welcome. Should I be worried because there's so many new faces compared to the last session when we talked about money and business and what kind of role would have on that kind of things? Today we will discuss about environmental impact in building sector. I promised to have some practical tools for low carbon design. We'll see what we have. We have 2 professors in here. Alan Organsy is one of the leading persons in developing wood and also decarbonized design in states. Matti Kuittinen is a new professor in Aalto University as well as the senior advisor on environmental issues in the Ministry of Environment in Finland. So if you have double role, Alan has maybe triple or something else as a practicing architect, also the founder of the design and build company JIG, then the teacher in the Yale University and Georgia Tech as well, and founder of the Timber City Initiatives, writer and researcher. So quite a lot in one package. Alan will start to remind us about the importance of the building in wood in urban scale, and the title is the Carbon Positive City. So,
Thank you, Pekka. I'm grateful to the Architecture Museum and to the friends that I know here and the new friends I hope to meet, and to Matti, who I've worked with now with Pekka at great length. If I'm either eating the microphone or holding it too far, somebody just wave at me. I'm not used to using 2 hands. I'm not ambidextrous. I want to start with a bit of an epilogue, or prologue, I should say, which is to show this print by Brian Nash Gill. He did a beautiful series of woodblock prints of trees in a book which I recommend that you get. But the reason I show this is because it is a little bit of the chestnut of the wood, no pun intended, the wood lecturer's chestnut. You know, you show a woodcut at the beginning of your lecture. Usually it's actually a picture of a tree, but this is actually an ink print of a literal tree. And what I like about that is that it's a bit of a dissociated, it takes away the sort of romance a little bit of the tree as this living thing. It's analytical. And I do that with intention. Because I want to talk about wood in this transcalar mode, which is to think about wood as a molecular, biochemical system, as a cellular system, and potentially as an urban system, and possibly a global system, but I'm really reaching at this point. So I'm going to be careful, and I hope you'll forgive me if I overreach. What I'm interested in is the potential synergy between 2 landscapes which have previously been considered in conflict, the city and the forest. And the thing to remember is that forests hold carbon and cities emit carbon. And so the question is there some way to game forest growth sustainable harvest to produce cities made of wood. And moreover, to try to disconnect from a building technological and industrial perspective two landscapes which are linked. The mineral extractive landscape, which produces steel and concrete, is linked to very efficient footprints, urban aggregations, urban building morphologies. And the forest, unfortunately, despite its incredible rich material range, is linked to a low-rise, low structural demand suburban morphology. So how do we break that? And what I'd like to propose is that we break it through regenerative architecture, and in particular, a regionally regenerative architecture, which cuts down on potential transport costs, which uses the feedback mechanisms of people living in forests or near forests to know if they're being over-harvested, potentially deforested. We've lost that connection. We talked a lot about that today at the World Circular Economic Forum, how people aren't paying enough attention to their natural surroundings, or I guess disturbed natural surroundings, which is most of the world. So the question really today is, how do we move from this low-rise suburban morphology, which is in America, suburbia, and it's one of America's greatest imports, or at least most durable imports around the world. We build suburban morphologies. How do we shift that material into new forms of building, which the Europeans have adopted much earlier than the Americans and the Canadians, but we're trying to catch up, and to produce high-density timber morphologies. And so I want to run this through because there's concerns about how much wood we have in the world and whether we can actually build global cities and why we would do that. And so we ran a little kind of scenario where we took a forest stand, and we planned to do a sustainable harvest, and we planned to build out a city, 4 blocks district in a city that I live in, New Haven, Connecticut. And you'll notice the comparative carbon content. And we basically ran this scenario where we made 60 plots. We cut 45, one a year, to build out the buildings based on the growth plan of the city. And we studied also the stem succession regrowth of each plot, and we calculated actually how much material was needed, and it was proved that actually the plots basically regrew, and we left quite a bit in reserve. And we started calculating how much carbon was actually moved out of the city. It started with how much was preserved in the forests that we didn't cut, how much was reabsorbed through the regrowth of the forests we did harvest, how much was sequestered in the buildings, and most importantly, how much was avoided when we didn't build with steel and concrete, which would have been the conventional building material for that neighborhood. And so we ended up with a total carbon bank of about 282,000 tons of CO2, which is equivalent to about 64,000 annual emissions of vehicles. And if you start calculating the current value of a ton of carbon, it's probably worth several $1 million. If you listen to Bill Nordhaus, a Nobel economist who described the potential for a carbon taxation scheme, he feels that by 2100, ton of carbon will be worth something like $1,000. So I'm not going to do the math for you, but suddenly we start thinking about carbon as an economic currency, and that forest is a driver of that and incentivized to grow and be protected and restored and expanded, afforested. And so that was my long-winded way of starting my lecture, The Carbon Positive City. Another piece of art by a really interesting sculptor, James McNabb. He makes a lot of wood cabinetry, and he started collecting all the scraps from a scrap bin, and he made a city, and he photographed it. And you know, art has something to tell us, I think, in this case. We should maybe be building cities with wood. Obviously, we should protect our forests, but maybe we should consider the possibility that we could build with wood. And so for those of you who are worried about global deforestation, I ask you to think about the fact that it actually may be a way to harvest silviculturally a lot of the forests that should be cut, obviously protecting those very biodiverse, at-risk forests in certain parts of the southern hemisphere. And in America, for example, in the US, at 1500 AD, half of the country was covered with forests. Today, we've removed a bit of it, and we're down to 33%. Right now, the US forests could sequester 11% of all the emissions associated with anthropogenic activity. But if we could potentially, with proper forest management, which includes use and harvest, we could sequester, absorb 30% of national greenhouse gas emissions. And you might ask, where's the rest of that going if the forests can't absorb it? We have other forest pools, other carbon sinks and pools, and we'll talk about that in a minute. But we should also start any discussion of using the vast usage of timber for building global cities, which will expand inevitably. We should talk about what the real forces today of deforestation are. Agricultural conversion. You know, we eat a lot of meat, fortunately, and we need lots of pasture land. And we mine for lots of things, lots of metals. We overuse metals, actually. We know this from our circular economic friends at the Finlandia Hall. And just building itself uses a lot of forest. And of course, climate change itself has wreaked havoc on American forests. You heard about the California lake, the Camp Fire in California last year, which destroyed huge amounts of forest and released enormous amounts of carbon dioxide. But this is really deforestation, because you can cut forests and they regrow. But this is what happens when you strip the soils, which have quite a bit of carbon in it. In fact, in the temperate forests, about 50% of carbon in the forest is below ground. And so when you strip those valuable carbon-laden topsoils away, you get an irremediable landscape. And we're running out of resources. We're talking about this at Finlandia Hall during the World Circular Economic Forum. We're spawning sand criminal syndicates that dredge illegally and collapse habitats in Southeast Asia to provide the demand for sand for concrete in India and China. And we accumulate waste, which is a problem in itself because a lot of it biodegrades, but we also remove valuable productive biomass by covering it with this, and we also cover it with other things, like cities. And we lose the value of those soils. Not to mention that if we keep growing as a global population at the rate we are, we will need 3 times the land area if we choose to build in the same way that we're building now in the same densities. So the question is, and I say this at the risk of possibly being mechanistic, could forests be a geotechnology? Could we treat them as valuable tools that we can work to solve a climate crisis? So I'm going to interrupt myself. A few years ago, more years than I care to remember, Pekka was very kind to invite me to speak at the Aalto Symposium 2012. And I titled my talk, Mistaken for Craft. And it was a sort of self-critique, because I came out of the cabinet making world. I was a furniture maker and a cabinet maker, and I started a shop, and then I had middle-class guilt and went to graduate school in architecture. When I got out of architecture school, for a lot of reasons, mostly a bad economy, I ended up going right back in and starting my shop again and doing cabinet work as a way of paying the bills. But I think it infected, or certainly inflected, the way I thought as a designer. I loved wood and its properties, mechanical properties, bending elasticity, hygroscopicity, all of these interesting properties of wood, and we wanted to play with it, and we also loved tools and tooling and how you can manipulate wood with adhesives or steam bending or all these kinds of ways of gaming the properties of a cellular material. But I think we also were very proud that we expanded our system boundaries of design and tried to think about sites too. We wanted to knit our buildings like a fine dovetail joint into every site we worked in. And then we wanted to make the experience of the wood part of the building that we were making. So this combination of scales felt like a kind of radical departure for us. I was a cabinet maker, but I was thinking about cabinet making at the scale of sites, building sites, and trying to knit buildings into them, while still taking enormous pleasure in very finely crafted detail. We're really proud of this house, and it is in an incredible site overlooking a sort of marine coastal landscape that's a lot like Helsinki, actually. And sometimes we actually used our houses to make sites. This was a sloping meadow that overlooked the Atlantic Ocean. It was kind of hard scrabble land, and we reproduced this for a big family of New York lawyers who had bought this incredibly expensive piece of property and asked us to make a house for them. And we used different techniques to try to be sustainable in the way we thought about the weathering of wood. And we learned that yakisugi, the charred wood technique, actually doesn't really weather very well, and it falls off after a while, and you have to retorch your house. I learned that in Japan. But you know, it's okay. And it was a big house with a lot of program, and it was complex, and we tried to be very disciplined about how we were going to make it work and fit into the landscape and create different places using, obviously, a lot of wood, and then looking out across scrub oak to the Atlantic Ocean and out into the forest around it. But, you know, the luxury of building houses like that, which are great because you get to learn how to detail things well. You're given the time to work iteratively and productively in the way you think about detail, and you make sure, hopefully, that they perform well too. But we had a chance to build a small building for the UN Environmental Program. We were asked in last May to produce a house for, they gave us a date in the middle of July, and we said, oh great, July 2019. And they said, no, 2018. Do you have a little house, sustainable micro house around that we can show at our high-level sustainability forum at the UN Plaza? And we said, yes. But we were lying because we didn't have it. Anyway, we followed all the SDGs, the Sustainable Design Goals of the UN Environment Program and Habitat, and we basically built a small building that could be trucked onto the UN Plaza. We learned later, after we'd already committed to this, that we weren't allowed to take a truck onto the UN Plaza, so that got tricky. But it was basically prefabricated in New Haven, and it basically housed a family of four for a peri-urban situation where there might be food insecurity, safety issues, power generation insecurity, no grids, and so we imagined that somehow it was a sort of post-apocalyptic New York. So we looked at the climate zone of New York and the material supply of New York, and we went to work. So we basically designed for about 4 or 5 weeks, and we built for another 3 weeks. We sort of started, and in 3 days we moved it onto the UN Plaza. And I will never recover from that. And if you've ever, imagine taking a house, admittedly a small one, through airport security. That's kind of what it was like. My daughter, who supplied us with food, almost got arrested by the UN police. And we looked at the carbon sequestration or storage of, which wasn't much, it's a small building, it's about 21 square meters. Really kind of one story with a loft. And we distributed the local material, and we looked at different systems, solar energy systems, solar generation, obviously, radiant thermal energy, indoor air purification, natural ventilation systems, potable water collection through condensation, but also through rainwater harvesting, and then finally a farming wall. And it was surprising to get it there. It's not, I wouldn't say it's a work of craft, but what it was an idea about working quickly with little time, trying to think on your feet, try to make a decent building, a good home for somebody with a lot of options. Essentially, you can kind of see the layout, I hope, and I won't go into much detail. This is the head of the Kenyan UN Environment Program, who spent a lot of time with us. He was great, and he actually said that he wanted to move in, which was nice. And we also studied exactly how the air we measured the air quality, and it turns out that wood has really high air quality once the initial VOCs have basically diffused. And this is our little mechanical room, which had 5 car batteries and could basically keep a family of 4 powered, enclosed in their house for 5 days, and produce enough water and enough electricity for that family to live, completely self-sustaining. And we used a lot of reused materials to make the sidings, and ran out and had to get new material. It was a rush. And we had a team of people in my office, students. We worked with the Center for Ecosystems and Architecture to develop the systems, and we made the plant wall and grew plants in that for over 2 months, and basically produced a pretty decent amount of nutrients. And it was a hit, because people in New York don't expect to find a house on the UN Plaza, and they liked it a lot. And this is the Deputy Secretary of the UN tasting basil and eating tomatoes, not the green ones. And so it was a good lesson in thinking more broadly about how buildings should perform, both as how they operate and how they protect people and provide them with services, but also how they should use materials from this increasingly resource-deprived planet. And so we thought about scaling up. And in scaling up, I like to think of sort of design spirit guide, Charles and Ray Eames. My partner Lisa Gray and I have worked together since we got out of graduate school, and we wish we could collaborate like Charles and Ray Eames, the great furniture designers and filmmakers. And I love this piece of art. It's a laminated double curvature sculpture, which I would love to have on my wall and own, but can't afford now. But when we add to the aesthetic program of this beautiful piece of sculpture, and we learn that it was a leg splint designed for injured soldiers in the Second World War, it changes our view of what that aesthetic is. It makes it more, for me, meaningful. Kant called that contingent beauty. And I think the idea of contingent beauty is something that we're wrestling with a lot, because of course we want to make beautiful buildings, but we want to do no damage to the environment, and that's the goal. And of course I was focused on the technique, cutting these little relieving joints so that the wood, which doesn't bend well in two directions, could bend in two directions. And what I really like is that the lesson that the Eameses learned was something about scale, and they did this famous movie called Powers of 10, which I recommend you see, which is essentially zooming in and out of human habitation on the Earth. And then they carried it into their work, scaling from a leg splint to a chair to a fuselage for a plane or a boat hull. And they understood that the beautiful thing about architectural design and material thinking is that it scales. It can scale, and you look for the lessons in the iterations of things that scale. And so we studied the idea of stiffness in a project, which we did in the late 90s, renovation of an old firehouse for an acoustical music studio, and we bought a bunch of plywood and we tried to see how far we could bend it in two directions. How stiff would it be? And we created an acoustical shell, and we modeled it, physically testing it using different techniques of sort of tuned wood mock-ups. We measured it and gave it to a Swiss acoustical engineer who promptly wrote back and said, I can't model this, it's too complex. And so we essentially used these different threaded rod systems to produce an acoustical shell that was acoustically dead for a recording studio and very live for performance, and that was a kind of complex design process. And we designed an acoustical diffuser at the stage to produce these sort of vanes which twisted and warped to diffuse sound for the musicians, and also to serve as an air return duct. And we stole a little detail from one of Charles and Ray Eames' furniture patterns, which was this relieving cut where we cut a circle out of the end of a kerf cut, saw cut, because we found that when we were warping that, it split. But when we could expand the tensile area around a larger surface area, it wouldn't split. And that became a kind of motif. And the room seats about 70 people, and a crush, and the piano you can hear. It's incredibly how live, how rich wood is, and we know it's a great instrument material. And here was a big room that was an instrument. You can hear the hammers on the piano coming down before it hits the string. And it's so incredible. And we were renovating this firehouse, which had been abandoned, and we were able to, through the brilliance of our client, Nick Lloyd, who runs a record label there, produce essentially a home for himself and his wife, who's a painter, and then their children, and a bar in the basement, and the recording studio, and the record label, and visiting musicians started coming, and it was really successful because of his vision. And he lived in this amazing sort of relic of 19th century New Haven industrial space. And he asked us, once he decided that he was going to house visiting musicians instead of making them pay exorbitant hotel prices in New Haven while they were visiting, he asked us to build a dormitory with 3 bedrooms on top of the building. And we quickly found out that the building couldn't support because it was an unreinforced masonry building. And so we chose to use mass timber, cross-laminated timber and glulam to stiffen the building with a light structural material that would essentially keep the building up under the load that it held. So we have a stairway up into a hallway and with a little seating area for musicians to play, a couple of 3 bedrooms and a little bathroom and a WC. And it's sort of created this new urban lawn on the roofs, and it's created more density. And what was the real discovery was we could plop this building down on top of an unreinforced brick building from, 100 years, built 100 years earlier. And so a developer contacted us and said, I want to add 2 stories to the other building next door. And we designed a sort of restraining system using cross-laminated timber cores to produce a hotel 2 buildings down. And then another developer called us and we designed another building, and I won't go into the details, but suddenly the city economic development coordinator was saying, oh my God, we can actually get more density in our city using wood because we can't do it with steel, it's too heavy, or concrete. So this is a great model and we'd like to pursue it. And that brought us to a kind of idea about this notion of structural biomass. Like why aren't we using this great plant material that's so abundant and so photosynthetically productive? It provides so many ecosystem services. Why aren't we using it for our buildings? Because we know that it will regrow, it will regenerate. We've been talking about renewable materials for 60 years. And so we began to study different scales of using just round wood to produce structure. That was a school. We worked to produce this apostolic community center for some Jesuit priests who said they wanted to be stewards of the environment and they wanted to be, follow their vows of poverty and celibacy. And that reminds me of a kind of funny story. We were having dinner with the rector, and we had a really nice bottle of wine while we were talking about the design. And another visitor who was a layperson, after this sumptuous meal, said, man, if you guys do celibacy like you do poverty, sign me up. Anyway, the building is a lot of wood. We designed it as a wood structure. The university that sponsored the building decided that it wanted to do a LEED platinum building, and we learned that you get more credits for recycled steel, despite the enormous smelting energies that go into steel recycling, than you do for a wood structure, because wood was essentially politically knocked out of LEED for quite a while. Recently it's been reintegrated through a material credit. And so we made a steel building and we used as much wood as we could, but what we found was that the university had essentially, through bad planning and soil management, had killed a few enormous American beech trees, which they were going to cut down and chip, and we decided to turn it into components of the chapel, because the Jesuits were talking about poverty. So we wanted to deal with this issue of scarcity through the wood, and we studied all the different kinds of flaws that exist in lumber and embraced them. Creating screens, privacy screens for the chapel and for the men between the public spaces and the more sacred spaces, and the altar and the ambo and the crucifix and the baptistry, baptismal font. And the idea was to embrace all of the material coming out of the forest, not just the superfine, the sort of rock star trees that everyone wants in their beautiful cabinets in Manhattan, in their kitchens and bathrooms, but to try to understand how we might use solid wood with flaw, with spalting and rot, and consolidate it into a meaningful piece of furniture. But the thing that really gets us excited is the technology of contemporary wood engineering and glue. And when we saw this, I showed this in 2012 at the Alto Symposium, when we saw this famous experiment, which Juhani Palasma called the man-made tree. We saw it as a sort of repository of lots of adhesives, lots of technically interesting adhesive. And we went to work thinking about all of the different things that are going on around the world, inventions, the sort of revolution in bio-based materials, biogenic materials, which is happening right here in Helsinki at VTT, or across the Atlantic at the University of Maine in Arno, which found a way to mechanically produce nanocellulose and are pressing panels out of it, or the work by the folks at the TU in Munich on cellular nanostructural modification of cell walls using polymers and mineralization to create greater rot resistance and fire resistance and all these kinds of exciting things, and these different techniques of adhering wood. We're even starting to look at lignin-based glue so that we're not actually using fossil hydrocarbons to make glue. And then Achim Menges' work at the Institute for Computational Design, where he's looking at the sort of natural hygroscopicity of the water-loving character of wood and how it can change to produce apertures depending on activated by moisture changes. But I like the dumb stuff. I like the stuff that's ready at hand that we're making. We've been making glulam beams for a century. We've been making CLT for 25 years. Petra, you can correct me on that, but it's been decades, let's say, we've been doing this stuff. And really the tool is a finger joiner to make long sticks and glue to laminate the sticks together to produce massive members with enormous capacity. And now we're only realizing that we can use them in the way we used heavy timber industrially in the 19th century. It's fire resistive. And it already knows how to manipulate the different quality of fiber that comes out of the forest by putting the best stuff along the structurally most demanding edges, tension edge, the second best stuff along the compression edge in a beam, and then you can kind of load the cheaper stuff in the middle, which means you're using more of the forest that you cut. And I think we haven't yet fully understood all of the potential of that capacity that we've been using for years, creating different kinds of structural configurations. And this is an example at Bloomer Lehmann in Switzerland, a 5-story building that the architects and the manufacturing company recognized that they were using a lot of spruce, which is a wonderful structural wood, but there's a lot of beech growing in European forests, and so how could they use beech? And they made laminated veneer lumber, bearing plates, and laminated veneer beech dowels to produce a 5-story building that had no steel. And so we started making lots of buildings out of curvy glulams because we liked the shapes, and we made houses out of it, and I think our clients tolerated it. And we misunderstood certain kinds of things aesthetically because we liked the shape of this beam lying on the ground before it was put up. And so we made a bridge out of it and sort of gained the capacity of the manufacturer to produce a construction bridge that is a 10-ton, US ton capacity bridge, which we watched a 30-ton truck drive over, which was very interesting. But what happened was it kind of sprung back into shape, and we thought, oh, wood actually is resilient structurally. And so we made a number of bridges, and I'll move through this quickly. It's a kind of passion of ours. We get asked to make bridges because people think wood bridges should be in woods. It's the, I don't know, correlation that people seem to like. And we really worked with our partners as glue laminators to produce essentially treated bridge systems. And we made our first suspension bridge a few years ago, and it was a challenge. Our company, Jig Design Build, rigged it. We have one of the builders here in the audience. But we got it straightened out, and we made this bridge named after Henry David Thoreau, one of the pioneer environmentalists in the US. And people use it, and they love it, and I think they love it because it's not made of plastic like a number of the other bridges up and down the river. And it's made of solid, thick material, which because there are not a lot of little joints, it's more resilient. It lasts longer. It's more durable. So mass timber has a lot of possibilities. And then, you know, the CLT revolution comes along, and the Americans figured it out, I don't know, like 18 months ago, it feels like. Meanwhile, Stora Enso and KLH and a lot of European manufacturers have perfected it and can still beat the pricing of American CLT manufacturers. And they just stole the idea of plywood, transverse lamination, and they produced it with sticks, as you all know. And you can produce all kinds of fascinating configurations. These slides are so outdated now, given what's available. I need to get on the stick and find some new pictures. But we're starting to build bigger buildings. This is the Arbora building by Nordique Structures in Montreal, 7 stories over a podium, 500,000 square feet, produced incredibly quickly. And meanwhile, we were building in the city these little tiny buildings, kind of bespoke community buildings, a merry-go-round building made out of just posts that canted to create structural lateral resistance. We gave them this engineers a nice thick roof structure so that they could use timber, and they made it out of steel anyway, because that's one of the issues. And we had a great fabricator in Quebec who worked with some Belgian and Austrian fabricator and French fabricators to produce this cupola made out of kind of topography of cross-laminated timber, which had 3 skylights and which sort of spun and rotated in the opposite direction of the merry-go-round. And it's the kind of thing that shows you that wood, because of the manufacturing capacities it allows, it's so amenable to digital kinds of fabrication that it's easy to build something like that in a factory, off-site, ship it, and with the precision to be able to produce this in a matter of days. A fabrication project done in a factory, but assembled by steel riggers, because the company that was the company Can-Am, which is the largest steel manufacturer in North America, has bought a timber fabrication company as a kind of climate change scenario, because they know that wood is going to be the thing of the future, and they know that their guys know how to lift really big pieces of material high in the air with cranes. And so we made this and built this building, and took a long time to convince anyone in the city of Stamford, Connecticut, which is a city of about 200,000 greater metro area, to build this for the kids. It's a public merry-go-round. It costs 25 cents to ride on, and they ride around, and I look up and I get a little seasick, but the kids seem to like it. So here we are. We've been experimenting with making wood in the city in kind of little stabs. Meanwhile, our friends in Vancouver and Austria are building multi-story, huge buildings out of timber, and we're playing around with one-story event spaces. But what was interesting to us as we watched the proliferation of wood architecture was the sort of molecular aspect of wood. It's made of carbon. Half of it is carbon. It's a carbohydrate, like spaghetti. And carbon is an interesting element. It's the 15th most prevalent in the world, and it's the 4th most prevalent in the universe. And it's called king carbon because it produces an array of different kinds of polymers at Earth's temperatures and pressures. And so it's abundant, hyperabundant. And when it's hard and transparent like diamond, in its allotrope of diamond, or soft and dense like graphite, you know that it exists everywhere in many kinds of conditions. A colleague of mine, an industrial ecologist at Yale, Tom Gradle, who's sort of one of the early thinkers about life cycle assessment and material flow analysis for industry, likes to hold up his cell phone and say that nearly all of the elements in the periodic table are in this cell phone, short of the radioactive ones, which is a kind of daunting thing to think about, given that most of the buildings we make today are much more sophisticated than our cell phones. They have much more material, a much wider range of material. And if you think about the throwaway culture of cell phones and you start applying it to building, it gets a little scary. So we could talk about all the buildings, all the materials that go into building, but I'd like to talk about carbon because that's the subject of my talk. And I want to just note, this is a great slide from Matti Kuitunen describing the different carbon pools that exist in the Earth, and that we've been playing a game where we have manipulated, if there was ever a homeostatic balance within those carbon pools, we've manipulated them. So that now we have a very limited time before we fully overload our atmosphere, already heavily burdened with carbon dioxide. And that's an important thing to remember. And we've seen since the Industrial Revolution a sudden spike in carbon concentration. And not surprisingly, if you also map global population against carbon concentration, you'll see that it's coupled. And that's the thing that people in the industrial ecology world and environmental world are worried about, because that means that when we consume as a species, we produce, not just because we breathe, because we make a lot of stuff, we're makers, homo faber, we emit carbon. And that correlation is very strong. And if you think about it globally, we know that over history, if you think of this as a timeline of the forest landscape, the biomass landscape that suddenly turns into the tall building, the Burj Khalifa is there. I learned from one of the engineers on the Burj Khalifa that when they pumped the concrete in the desert heat up to the upper floors through a pump line, they had to actually jacket the pump with ice water because the concrete would overheat and cure. And I think when you are making a building in which you have to put ice, you have to ice your concrete, I think we're in a very serious societal problem, economic, political problem. And in doing so, we've actually dug down through that precious layer of bio-rich soil to create a kind of hole for ourselves. And then these are all the different material classes. We start with wood and we move all the way down to the fossil hydrocarbons that fuel manufacture. And we learn basically that we have dug ourselves into a deep hole, existential, environmental, global. In fact, it's been noted by many scientists that human beings have now disturbed every geobiological, geochemical, and geophysical system short of the tides. Anyway, back to my point. Sorry about that. So this is a strength-to-weight ratio of concrete and steel and wood. And we know that wood has a really high specific density, strength-to-weight ratio. But if you take into account span versus carbon emissions or carbon footprint, you learn that a wood beam actually spans a lot longer than a piece of concrete. And it's a sort of conceptual model, but basically what we're saying is you get more environmentalism, less carbon footprint for the spans that you get out of mass timber, which should be an economic incentive for anybody. And if you just remember that basically half a metric ton of carbon is stored, carbon dioxide is stored in a metric ton of mass timber, or choose your unit, we can start thinking about how wood, as well as carbon, can be a bit of a currency. And so I want to tell a story, which Matti will be commenting on soon, about a school that we made. It was a farm school in New Haven, Connecticut, serving inner city kids who have very little access to farms or nature, and they study ecology and agriculture. And they asked us to build a building for them on this site, a former farm site. Their classrooms were here in this old building. There were their farm fields. Basically, it was a dump that had been excavated out of a mountainside, and so there were lots of drainage problems. And they asked us to build an ecological building. And so we designed a classroom building which had a gym. They could only afford a half gym, art classrooms, 2 science classrooms, offices, and that it would create a new space of entry for the school because they were parked on a hillside. And so we used the building to navigate that sectional change. And it's fairly simple. I won't go into too much detail, but just to give you a little reference, the building has this half basketball court, which also serves as a gymnasium and a rec space and a theater. And then most of the offices and bathrooms are downstairs, and then upstairs are classrooms, which each look into different areas. And we decided that we're going to throw everything at this building. The roof was going to become a really important element in the building. It was going to allow, obviously, natural daylight to reduce electrical illumination costs. It was going to be super, super insulated and airtight so that we could optimize our thermal performance. We lined it on the south. The roof pitches optimize the angle for solar photovoltaic arrays, which would power the geothermal pumps that ran the school. I mean, it's really hard. American school systems are a wreck. So the idea that a public charter school could get the bond issued to produce the school was a big deal, and it was really a tribute to the administrative team. They were incredible, and we've got all this stuff in there, and we developed bioremediation pools and artificial wetlands, which became outdoor classrooms. But we argued that the thing that would be the most beneficial was to use regionally harvested wood to build the building and to use it as densely as possible and to use these new technologies that would allow the structure to be the finish as well as the structure, that we wouldn't have to cover it up. And so we looked at black spruce from Canada, not too far away from us, about 580 miles, and a manufacturing company that was using this black spruce that grows in little thin strips, 8 inches in diameter maximum, very tiny. No one in their right mind would harvest a piece of wood like that. But that's where they work, and they figured out really wonderful lamination systems. And we studied how long it would take to optimize growth, how to optimize carbon sequestration in the forest, when we should harvest it, how much carbon would be stored for all the species that went into the building. And then we began a kind of transfer of that material conceptually through all of the different products that we were using, from finishes to structural components, into the building, and we tracked exactly how much carbon would go in and through the forest. So this is what we are calling the carbon transect. We measure off that line. This is the stored carbon. This is the emitted carbon during production and transport, and this is the carbon that gets stored through the body of the building. So we learned we get to store quite a bit of carbon. And we took into account the fact that the material was manufactured in Quebec, produced in Walpole, New Hampshire, and then shipped to New Haven. And this is the story of the construction. 5 guys and a crane. The whole assembly was put together in 2 weeks. And then the sidings went on, and we learned that, there's a whole way of getting more advantage, getting more to optimize more the prefabrication, which we would do next time. And the building now functions for 220 high school students and 15,000 New Haven residents every year through different kinds of programs, camp and farming programs. And the building is made out of wood. This is a glue laminated bridge which replaces what would have been a concrete egress stair. And we have a little bit of steel in there because wood can't do, when architects like to make things very thin, wood might not be able to do that. And the building is lined with cross-laminated timber. It's really an industrial product. As if there were an exposed brick wall, we would love it, right? But wood structure, people don't think about so much. These are just big plates of wood that reflect light beautifully, treated very cheaply for this rather resource-deprived school. And all the sort of public circulation spaces are made out of wood, cellulose fiber, and there's some concrete in here too. We'll be talking about that. It's really interesting. When we finished the school and we wandered around and the kids were talking about all the ecological principles that went into it, we would ask them, what do you like most about the school? Hoping that they would say, oh, the daylight is beautiful. Oh, we love the shapes. The roof shape is so cool. To the one, they said that they thought the building smelled good. And that was an insight that we started thinking about a little more, about this idea that we know about through the work of great people at Aalto University, that the absorption and desorption of ambient humidity, because wood likes to give off and absorb water, actually stabilizes indoor air humidity, which might lead to less sick building syndrome and a natural way of buffering swings in ambient humidity. And we've also learned that with this property comes a phase change from vapor to liquid in the cells of wood, and that may have energy implications, so-called hygrothermal mass, which is just being studied here in Aalto University and other places at the Norwegian University of Science and Technology. Christina Nora is a colleague. But basically it's just a building, right? It's a building that could be built out of wood easily. It's not a big deal. It happened to be one of the first buildings in the US to use cross-laminated timber, but it's otherwise just a nice place. We're proud of it. The kids seem to like it. The teachers like it. They celebrate graduation inside that room unless it's really sunny, and then that's where the speaker stands, but there's a kid playing basketball. And it's a farm school. But what we decided to do was, with the help of Matti Kuitunen, is essentially conceptually take the building apart to try to understand what its impacts really are. And so through this carbon book project that Matti and Pekka and a colleague of mine in the US are working on, we started studying actually the impacts of the building. And we looked at what elements in specific were emitting carbon, and Matti will talk more about this and with much more insight than I can offer. And it's, as you'd expect, electrical elements require a lot of heat for formation. Site and groundworks can just disturb a lot of soil, and we pave things, so we lose carbon that way. And concrete foundations are a big producer of emissions. But if you look at storage, now it shows a different picture. These offsets start to become really valuable because the wood material and also the plantings and the new very productive soils that we tried to protect with the farmland and with the wetlands actually can store carbon. And so we made this sort of monstrous drawing, which is everything below the line stores carbon, everything above the line emits carbon, and if it's bigger, it stores more carbon. It's one of those useless drawings that architects like to make. I like it a lot. But it's really a way of saying that there's a monstrous condition happening, which is that we can store and emit carbon at our will, and that at our will is a really important part of this discussion. And this young guy worked on a study with us. He took our building information model, we taught him how to do it, and he quantified all of the material, and he counted up all the weight of the wood in the building, and he learned that there was 450 metric tons of carbon dioxide stored in the building, which is worth 100 cars' annual emissions, which is a great project-based educational opportunity for kids. He was I think he's going to be a major scientist. This guy was amazing. And that brings me to really the end of what I want to talk about, which is this idea of bioeconomic building scaled up to some of the themes, and this relationship we talked about. And I quote Lionel Robbins, who is the founder of the London School of Economics and who defined economics as a science which studies human behavior as a relationship between ends and scarce means and alternative uses. And that's what we're talking about today as a planet. And so we took our common ground model and we started studying exactly how much carbon we could store, how often we could replenish a harvested forest cut, how to move those forests of different species through our commercial products that are available right now into buildings. And we looked at suburbs, more suburban kinds of structural morphologies and assemblies. And then we looked at high mid-rise buildings. And you can see, remember my carbon transect, that below this line are the storages. So this upper line is a reflection of cyclical growth and death of forest fiber, which emits carbon. So whenever it jogs back up, it's emitting the carbon because it's rotting aerobically mostly. And this is what happens if you don't let the forests, the logs lie in the forest and rot, but you actually use them productively. Again, I'm showing my technological bias, so forgive me. This is what's stored as we shift this material into these large urban buildings. And so we thought, okay, what would happen? And this is just a thought exercise, so forgive me, but we actually did a paper called Building a Global Carbon Sink with a group of European scientists and some American scientists. And we basically tried to imagine how much wood we would need to build all the buildings required to house the new global population explosion, the next 2 billion people who are going to inhabit the Earth. And this, again, is a carbon transect. Below it is carbon absorbed and stored. Above it is carbon emitted. This is already out of date. This was drawn in 2017. We've surpassed 400 parts per million in the atmosphere, which is 50 parts per million above what is considered a sustainable density. And that's the 2-degree that we came up with, the 2-degree temperature rise, which has now been revised by the SR15 IPCC report to 1.5 degrees so that we can save some of the Pacific Island nations from being over-inundated with seawater. And then we looked at how much carbon could be sequestered if we built all the new, just buildings, occupied buildings, not infrastructure. And it was an estimate, of course, and we learned we could, basically within a range, store about 5 gigatons of carbon in the built environment, which, by the way, we're going to build anyway, right? So it's either going to get emitted or it's going to get stored. And then we looked at what would happen if we use this biomass scenario. What would happen to the upward accelerating curvature of emissions? And we found that we bent it down. Now, this, again, is an average, so you have to forgive the license I'm taking in talking about this. The point is, we're going to build a lot of buildings, we're going to emit a lot of carbon, and we can store a lot of carbon, and if we can forest the world's forests, the right forests, sustainably. So that temperate zone, and the boreal forest here is going to be an important provider, and we'll use the mechanisms of global economics and exchange to hopefully transition to post-agricultural waste products in the global south where there's less timber. We have a colleague in Indonesia right now who's making rattan glulam, which is a weed. And so in a sense what we've done is we've rewritten the history, or we're rewriting a future history of global carbon. Starting with the Carboniferous era, where the fern-like trees and the sort of low number of aerobic bacteria that wouldn't digest cellulose basically consolidated into this vast fossil hydrocarbon pool in our lithography, in our lithosphere, and to the point of the Industrial Revolution where we start digging out that fossil hydrocarbon and emitting it to build our buildings and fuel the manufacturing processes. And then finally, through a new set of kinds of assemblies that maybe we can use, again, carefully, to produce a new biospheric building, which relies largely on renewable resources as well as industrial waste streams. So to this economic exchange, we know in the eastern seaboard of the United States, I think it's less of an issue in Finland, but in the US, we have flooding all the time. And architects love to adapt to climate change. They talk about resiliency as a means of getting more work. We can build our way out of this problem, and yet we'll just exacerbate the problem in the process. I'd love to do the life cycle assessment on this concrete seawall. It will certainly last for a while, we hope. And then the other option, which I think is less considered by architects and environmentalists, is that the built environment could mitigate climate change, which is what I'm talking about. And what does mitigation look like? It probably looks like a robust forestry, sustainable forestry system, incentivized forest restoration and afforestation, growth of new forests. And it has a lot of great, hopefully pleasing wood architecture in beautiful convivial densities like Helsinki. Thank you.
Millions of questions in my mind, but do you have any in the audience? We might have few before Matti starts, or should we leave them at the end? Any burning questions? Anyway, one of your subtitles was something like mistaken by craft. I think Matti's title is much more forgiving, do no harm. I don't know what it means, but we'll hear about that.
Hello, good evening everybody. So as I was already introduced by Pekka, my name is Matti Kuittinen. I work in two instances. I work at Aalto University as an adjunct professor starting 4 days ago, and at the Ministry of the Environment as a senior specialist. So that blends the two professional loves of my life, policymaking and teaching and academia. But today we're going to talk about something that has its roots not in architecture but actually in medicine. The phrase here, do no harm, is attributed to Hippocrates, the famous Greek father of modern medicine. And in his writing you can find this phrase, and he talks about that when a doctor is treating a patient, he or she shouldn't cause more problems than what the treatment is meant to solve. So we don't want to end up too often in a situation where the operation went great but the patient died. So that's normally considered to be one of the goals of medicine. But this principle, however, lends itself very well to other fields of life as well. For instance, in humanitarian work, of which I have a little experience, it's often used and often kept as a principle. So when the Western wealthy people go to a poor, underdeveloped country to help them to get over an earthquake or something, they shouldn't cause more problems than they're trying to solve. I was working in Haiti after the earthquake, and there were peacekeeping forces, UN peacekeeping forces from Nepal, and they of course kept peace, but at the same time, unfortunately, they brought in cholera, which is not typical of Haiti. So they tried to do good, but unfortunately, they did something else as well. So the do no harm principle also lends itself to construction and architecture, and maybe today it's one of the key questions, at least from policymaker viewpoint, when we talk about construction. Because we use half of all global raw materials for building. During this century, there will be around 11 billion people living in buildings that are not yet built. And we can't keep on increasing the use of natural resources for construction on the same rate that we do today, because it's causing at least 1/3 of all global greenhouse gas emissions, and it's not tolerable. So we need to change the way. I suppose that many who are here today are architects as well as I am. And we've been trained to get our living by designing new buildings or planning new cities. And if we are to cut drastically down the emissions that are attributed to building sector, how are we about to do that while keeping on what we are taught to do, designing buildings? That is a very big and fundamental question. And I hope that we can discuss about it today. So to put that in sort of like formula, we can talk about increasing or at least maintaining the quality of a building while cutting down the harmful impacts of the building's life cycle. So this is like pretty self-evident that this is the way to go. However, the task ahead here in going down with the harmful impacts is very large and very challenging. So we can take a look at that from the viewpoint of resource efficiency using a term called decoupling. Now there are two ways of decoupling things. The first one is called relative decoupling, and it's used in resource efficiency to describe that ideally the gross domestic product should increase while the environmental impacts or harms are increasing, but not as in a steep curve as the gross domestic product. So this is called relative decoupling. This here, absolute decoupling, is much more favorable. It describes that the GDP goes up while the environmental impact goes down. So this is where we are aiming at, and this is where all the societies should aim towards. Then if we take a look at this from the viewpoint of greenhouse gas emissions, it's been suggested that we should cut down the global greenhouse gas emissions 50% every 10 years in order to avoid very dangerous and very, very expensive climate change. And this is interesting when we try to see that how can we make this happen in the buildings that we are designing and building. And this leads us to ask the question that how would architecture look like if we would need to halve greenhouse gas emissions every decade? Now think about the chair in which you are sitting. Think about that if the same chair designed in 10 years would have to be done with half of the materials that it has now. What sort of chair would that be if there would still be a need for a chair? Now that's of course rather superficial like thing to say, but anyway, that explains maybe something of the challenge that we have ahead. So it's a question of architecture and it's a question of process. How can we make the buildings work and maintain much of their functions while creating much less environmental problems? Well, one thing is for sure, we must get away from the linear thinking that buildings are just consuming energy and materials over the life cycle, and we need to change into a circular thinking, especially in the construction sector, where the material flows that are put into the built environment are again reused and recycled, either into new construction products or at least into energy that is fed into the system and sustains the built environment. But to bring more perspective, I'd like to take you to a case study. It's Alan's and Lisa's wonderful school. It's a very nice building. And I had the privilege of getting full access to the building information model and all the material, bills of materials of this building. And together with my colleague at Aalto University, we made a calculation exercise. And we tried to figure out that how large is the carbon footprint of the building and its site. And then we wanted to know if it would be possible to reduce that without touching the architecture and the geometry of the building, of course. And then we want to see also that how large are the carbon storages and sinks around the building. So now, unfortunately, we are going to the boring part of the presentation in which I'll be showing graphs and figures, but let's hope that you can tolerate that while after having seen so much of the eye candy from Alan's previous presentation. So let the boredom begin. Here is the share of emissions from the building over a 50-year life cycle. Now, less than half of the emissions come from the operative use of energy, from the heating of the building and for the electricity, and over half come from the production of construction materials, construction work, and so forth. So the balance has already shifted from use of energy to these so-called embodied emissions. To explain that a bit more, I'm using this sort of graph. You saw that on a much more eye-friendly format in Alan's presentation. Everything that's on the right-hand side here on orange and red are emissions, so these are bad things, and the green ones here on the left-hand side, these are good things. So here we have all the parts of the building, and here we have how much emissions are caused from these building parts. Two interesting things. First of all, electrical elements, mostly solar PV panels, are the single biggest source of emissions in this building. And that's interesting because today we are hearing that, yeah, we should load our buildings with solar PVs and we should cover all the possible parts in cities with these. But we should think about also the principle of do no harm in this instance. And then the second interesting thing is that the site and crown works, these seem to cause relatively much emissions, although there is also the potential for sequestering carbon on the site. And now let's take a bit more detailed look about these. So first, if we take a look at the site, as Alan described, there used to be a site without any buildings, some trees standing there, and then there was some soil removed, some new soil and gravel brought in, and some asphalt roads done, and some concrete paving done, and the building was built. And while this was done, there were lots of emissions, mostly from the making of asphalt for the roads, but also from concrete paving and plastic pipes and so forth. And in the graphs on the following slides, I'm going to show you three things. First of all, the emissions, then how much carbon was either stored or sequestered, and what could have been done otherwise. What could we avoid if we chose a different approach? So we can see that if we just look at the site, it's the asphalt road and concrete paving that cause most of the emissions, but luckily the soils of the site in this building, while the building is being operated for 50 years, there are herbaceous plants, there are grasses, there are trees growing, and all these natural processes or ecosystem services, they accumulate soil, carbon from the atmosphere into the soils. And that's actually pretty much, it's actually more than what the production of asphalt causes. So lesson number one, we shouldn't underestimate the role of ecosystem services in our building projects, and this is something that is very poorly understood, especially in the urban context, unfortunately. Then, second thing, foundations and ground floor slab. Here we can see that most of the emissions are caused from the concrete used for these building parts. There is very little carbon to be sequestered. But if we would have used greener cement mix in which we could use cement substitutes such as fly ash or blast furnace slag up to 25 or even 50% of the amount of cement, we could cut the emissions from the use of concrete into half. And that's something that this is a big number. We should aim towards this. And in the end of the presentation, we will see if this is truly enough, if we would need to cut the emissions half every decade. Then let's take a look at the structural frame of the building. Here, most of the structure is made from wood, CLT. There are some insulation materials and very little amount of steel parts. But you can see that these cause very, very little amount of greenhouse gas emissions, whereas there is huge carbon storage in these materials. So if you could account this as a benefit, you could see that this actually has a positive impact. Then if we look at internal dividers in the building, and these things are something that you typically need to replace or at least repair during the use of the building. So that's why the materials make a difference. If we look at these, we can see that there are some emissions from the production of gypsum boards or CLT for the walls. But there are also lots of carbon stored in both wooden frames of the intermediate internal dividers and CLT materials. And if you want to be really nerd in trying to tweak your carbon footprint to as small as possible, then you could speculate on changing old gypsum boards into wood panels. But then again, you need to realize that in a typical construction project, you have other aspects than just the carbon footprint. There are fire safety, there's acoustics, and there is also the price. So gypsum board today is positioned so well in the cost optimum of construction materials that it's really hard to defeat in the construction markets. Then finally, this building, even though it's an old building, it's lots of building services, electric cords, ventilation, perhaps cables and ducts. And so does this beautiful Common Ground High School in New Haven. And the interesting thing is when we calculate all these and sum it up, that shows a remarkable impact on the carbon footprint, especially the solar panels. The impact of making these is huge. However, there are good news. There are so many ways of making solar panels. These are made from monocrystalline PVs, which is one of the ways of making solar panels. It's the most common today, and it has the best price to kilowatt-hour ratio today. However, if they would use thin film solar panels, we could cut this emission into half, while keeping roughly the same level of renewable energy sequestered from the roof of the building. So I think here architects and engineers and designers should pay attention to what are the options of harvesting renewable energy in the building, because that can really lead to making harm or making no harm in the building. But still, if we are using these solar PV panels, the monocrystalline panels, the emission savings with these are huge, nevertheless, of the emissions that they are causing in their production phase. Now, depending on what sort of scenario we are imagining for the electricity's carbon footprint in this area, using solar PVs in the building can save from 370 to almost 1,000 tons of CO2, because you didn't have to purchase electricity from the grid. That has a certain carbon footprint in this area. So even though they had a big carbon footprint, that was an investment worth making. Then if we sum up all the mitigation potential that we have in this building, what could we have done otherwise? It seems that greener solar panels, this is the greatest thing that you could have done otherwise, and greener cement mix, obviously. And then if you switch gypsum boards into wood, that has an impact, not that large, but it has an impact. And if you could use recycled asphalt on the side, that would also make some difference. But the big gains are here. These are the low-hanging fruits that we should, in the next projects, and maybe you are also already taking these into account. Oh yeah, that's great to hear. So these mitigation potential, all summed up, is some 1/5 of all the emissions that are caused when the building parts were manufactured. Now that sounds like a big number, but unfortunately when we scale that up to the life cycle emissions of the building, it's only 4% of these emissions. And this leads us to ask the critical question that what if the building would have to be designed with half of the carbon footprint? How could we reach that? The good news, however, is that most of the emissions are a consequence of direct design choices. And those of us who work as designers or construction managers, we have a great potential and a great opportunity of influencing these emissions. So we truly can be the good guys in this battle towards climate change. Now, to sum it up, where is the ratio between the quality and the harmful impacts? Are the harmful ones winning? We can say that, of course, there is lots of quality in the architecture and function. There's lots of environmental quality in the storage of carbon and uptaking of that on the site. And there's lots of quality in the energy efficiency and use of renewable energy. However, we have life cycle emissions from the construction, and we have emissions from the land use change. It used to be, well, relatively close to natural state, at least there were trees growing. So there is a change of the land use and land occupation. Now, let's get to this question. If we compare the emissions, the harms that the building is causing to the good things, the sequestered and stored carbon, we can see that it's actually, this is half of the embodied emissions. But still, even though this building, up to in my opinion, is a very high quality building, it has very good technology, it has very wise design choices, still, it's not doing that well And this is not a fault of a designer. This is something for the whole construction sector to tackle. Because it's impossible for an architect to make a building that's a saint if there are no raw materials or no products or processes for making that happen. It doesn't matter how beautiful dreams you are putting on the paper. It's the construction process and all the procurement decisions along it that either make it or take it. But the interesting thing is if this is like the state-of-the-art, excellent wooden school in USA today, in the 2020s, how could we make it happen in 2030s if we would need to cut down the emissions into half, into something like this, or 2040s, or 2050s? Let's imagine that we could use just zero carbon footprint electricity for the building. We could have, let's say, wind power or something that would cut this off totally. So we would be left only with the embodied emissions. So if that would happen, then we would be fit for 2030s. But then the real trick is to get to 2040s. And if we assess the building that we can cut up to 20% of the emissions of the production phase of the building by changing the materials and making more sustainable choices, it's still a huge task to reach this, or even this. And without touching the architecture or the geometry or the functionality of the building, it seems impossible. And that for designers is a really big question, that how can we satisfy the user needs, maybe with much less space, or maybe without building anything, maybe by occupying an existing empty space somewhere and trying to make that fit to the purpose of the user. I'm working at the moment with the revision of landscape and the construction regulation in Finland. And somebody from the stakeholder group asked the question that should we make that sort of proposal that if you want to build something new, you should have first figured out if there are any existing buildings. So there would be a ban of building anything unless you cannot show that there are no existing buildings into which that function could be placed. And that's a big thing to ask. But then again, if we were to reach this, how is that ever possible? Of course we can say that, okay, it's not, construction sector doesn't have to reach these things. The other sectors will do it. What other sectors? There is no way that the transport sector could go negative in its emissions. You cannot think that, or maybe somebody can figure out an airplane that's sucking CO2 from the atmosphere while it's flying. Or maybe you can figure out a food sector that's negative in terms of carbon emissions. But I mean that where is that other sector? And if there is another sector that is fully carbon negative, how much do we assume that would be the cost of compensating emissions for the sake of making buildings? And what would be the impact of the construction prices? And again, to living costs in cities. These are very big and fundamental questions that are not yet clear. But let's get to this. We should do no harm. We should think about these things while we are designing buildings. In my opinion, we should try to stuff as much carbon from the atmosphere to the wooden or bio-based parts of buildings while we design them. That seems to be one of the best options for making new buildings in the future. At the same time, we should make sure that we maintain the natural habitats in the state in which they can sequester carbon from the atmosphere, because this is by far the most easiest and cheapest way of removing carbon from the atmosphere, putting that into growing forest. Now, I have spent my time, and I think that maybe now it's a good time to maybe continue discussion with all you. Thank you very much.
Sometimes these lectures about environmental impacts turn to doomsday, but you brought a lot of good news. But what is your opinion? Is there more bad news or good news?
I fear that we have a huge task ahead of us, as Matti has identified, and working as a practitioner, as well as someone who tries to think outside of practice. The guys I work with on construction sites their bottom line, their bottom dollar is the primary interest. In the American building industry, which produces a lot of building, how can I put it? The craft of building is no longer a priority. And the economic instrumentality of building has become the priority. And so that scares me, honestly. But then again, I met Pekka and Matti, I don't know, 8, 9 years ago. And in that time, the changes that I've seen in the wood industry in the US are significant. And what's more, it's captured the interests and excitement of builders, developers, architects, and most importantly, my students. And I think that's promising. And then what we talked about today at this conference is that there's a problem of people unlearning habits, conventions, and it's hard enough for me to, I don't know, drive slower, eat less, you know, those are hard. But when you have a gigantic economic system, a political power structure, cultural biases, those are hard to shift. And so I think our challenge is what's being asked today at Finlandia Hall, which is how do we rethink our activities as human beings, which is exactly what Monty's saying. I'm not going to say I'm pessimistic because despite my doom and gloom personality, I have hope that we'll be able to solve it, but I think Monty has very succinctly described the challenges of that. So I'll let you take it. Looking more optimistic.
Yeah, of course, I'm very optimistic since, after all, we created this problem, so I suppose that we are able to solve it. So it's not a force of nature that made this. It's not an alien species that invaded the Earth. It's us. So we can do it. I don't think that's impossible at all. We just need to shift the mindset. And I think that if you want to look at this from the positive perspective, I think that the shift to circular economy and sustainable lifestyle, it's going to happen anyway. But the tricky thing is that there are two paths that lead there. There is the path that assumes that we can quickly change our policies and our behavior so that we can do the shift in a controlled manner. And we can all be happy and prosperous even. And then there is the path in which we see that the negative impacts of changing climate and the negative impacts of the Anthropocene, they become intolerable to human nature, which may lead, as we already see today, into rise of political turmoil, populism perhaps, which weakens the decision-making capacity of our societies. And we end up in struggle for resources on the planet with more people on it. But also in this scenario, we will end up in circular economy and sustainable lifestyle, but the problem is that we are going to hit the wall before that happens. And that's going to hurt economically, socially, and on human level. So either way, I believe that that's the future, but it would be so much nicer if we could choose path number one.
By the way, to me this was a perfect combination of research and design practice and emphasized the meaning of the lifelong learning. And thanks, Alan, for volunteering to be a guinea pig on that Matti study, which didn't always look good, but next time it will be, of course, much better. How did you feel about that?
Thank you, Alan and Matti, for the great lectures. I would have a question because let's say that as architects, how much we can do. So my question would be, how do you, watching your projects, I was thinking about the symbolic meaning of them. Obviously, you have made your breakthrough in the US, and your school is like one of the, well, it seems we are looking at it right here across the Atlantic. And so what would you think about this symbolic meaning and importance of your work? Do you see any importance on those things?
Is this working? Yeah. Thanks, Antti. I guess I would say, I'd quote the former dean of the school that I teach in now, Paul Rudolph, who said he never talks about design with his clients. Obviously, there's an enormous interest in the cultural meaning, impact, symbolism, significations of architecture. And I think that gets to a point that Matti has made really articulately in papers he's written, which is decoupling is the separation of quality from harmful impact. But part of the quality that I think you're advocating, if I can speak for you, is that the architectural, the symbolic character, the meaning of the built environment is as important as its environmental, its lack of environmental impact. It is interesting that I think I used to talk more about our work and think more about our work as an art project, an art practice, a cultural practice. Now I think I've become a little more of I think really hard about what I'm doing wrong, about the doing no harm. And so I tend to talk about it that way. But of course, as you know in your work, all of these issues of how people live there and how their children play and what the shapes of the buildings that we make, whatever they are how they're enjoyed. And those are deep in our work. That's a big part of it. Otherwise, we just build ticky-tacky boxes all over the place. And sometimes end up having to anyway. I've done my share. So I think that's a really important question because I think the way, for me, what's meaningful about hearing Matti talk about the work and having basically been undressed architecturally by him, is that the stakes are high environmentally, but the stakes are high culturally. We can't debase our built environment aesthetically. We can't debase it in terms of human experience, in terms of safety, in terms of all the things that we think about that give meaning to architecture. Because then environmental low impact work creates another kind of environmental depredation. And so I think that's, I don't want to diminish that side. I mean, I hope you can see from the work that the small projects that we've done, that we care a lot about that. But I think I have to front load some concerns for my kids and their kids and my friends, because I just think I want people to know that it's not just a discussion of culture, and that's important.
Without touching the architecture, should we touch the architecture?
Well, you should ask an architect, perhaps. But I think that it's a question about how much space do we need to fulfill our functions, and could we be wiser in that? Pekka, we've been teaching together at the Wood program for many years, and I remember when I started as your assistant many years ago. Yes, yeah, but I'm having a point here. And the point is that I remember when the first Japanese students came in and they started to make their sketches and examples of how you could redesign a sauna or something else. And I was like, wow, how can you really stuff so many functions into such a small space and layer them on top of each other and make a multifunctional space? That was a really eye-opener for me of seeing the richness in different design cultures and design contexts. So I'm very confident that we have not yet reached the bottom in the tank of architectural possibilities. There are so much more to come.
So that brings us back to your question, which is that I think the thing that I'm most thrilled about is the idea that the invention, architectural invention, that will be driven by resource scarcity. That seems to me like a really, that's what my students are excited about. That they can go to work to solve problems that are more than the marginalized aesthetic concerns of a certain class of people, but that they actually are having an impact. And that has the cultural meaning that you raise and the signification that you raise. I have been working in Japan, and I know that we can make buildings smaller. I think we can make them simpler. They can weigh less. They can be simpler across the supply chain, fewer steps. So all of these things, I think, are part of that. And I revel in the new architecture that will produce. So I would even say, I think they should change. I want them to change. I'm excited about being part of that process.
By the way, just for information, we have still 4 lecture sessions left, and not all the lecturers are not my friends.
So you are inviting some of your enemies as well.
I will keep on asking a stupid question if you don't do it. Matti has something to add.
Yeah, just a small addition, if I may. I've been reading about, from the behavioral psychologist, papers about minimalism or voluntarily simplicity. And that's actually rather interesting, because that minimalism is one of the trends in architecture, even quite often it's fashionable. But it's an interesting question that since this is a trend among well-educated middle class or upper middle class Western people, they want to live a more simple life in a beautifully designed, very empty-looking apartment. Could that be one of the paths that we could use as a fuel for architecture of getting more with less materials?
We're suggesting finally finding the answer for the question of whether less or more. Fred, you have something in your mind.
We have a saying in English that when the going gets tough, the tough get going. And I'm beginning sitting here and listening to you guys who obviously put a lot of time, a lot of care into what you're doing, and you're extremely well motivated. But my question to you is, we belong to a very, very small minority of people on this planet. That's one problem. Second problem is, we need to accelerate the changes you've been talking about. And how do we actually do it when 70% of the world's population are hell-bent on becoming as big, if not bigger, consumers than we've been? And I think I'm not saying architects, the contribution we're going to make is fairly minimal at the end of the day. But how do you see as educators, as let's say middle-class do-gooders, how do you see this process accelerating? Because we need to accelerate it, and really, really fast.
I think this is one of the quick questions, of course, and one of the answers that I've come across is economy. Today we are seeing a boom of green bonds and green financing, luckily, and that may tick the box that reads greed, and that's one of the best motivators for man, to get more money. And luckily investors are coming up with more and more mechanisms for sustainable financing and green bonds. And these are becoming very popular also in the construction, infrastructure and energy sectors. So it might actually be that the business is solving part of this problem. It's getting more profitable to invest in green projects. You get much more revenue from them. It's not, of course, going to solve everything, but that's, I hope, part of the problem, because it's money that makes the world go round, and I hope that it's going to make it turn around into a better direction. Then you said that we are a marginal part of people. We are architects or something. We have something to do with construction, and we are from Western country, well educated ones. But I think that it's our moral attitude to do something for two reasons. First of all, 50% of global raw materials go through our fingers or through our building information models. Secondly, average Finnish carbon footprint is 10.4 tons per year. It's over double of the world average, which is many times too big. That would have to be smaller as well. And maybe a third point would be that Finland, as has been repeated often, and while the new government has been getting all its skis into the same direction, Finland can be a bigger player in the global sector than what it's actually its size. So we could at least try making a good impact.
We will give you practical tools, did we, or did we cheat you? What if we did? Is it still secret that you're publishing the online education package about these issues, or now I said it all?
Yes. Yes, tomorrow we launch the Decarbonized Design website, which has several components, open source learning materials, wonderful lectures by Monty, which you can download, curricular materials for graduate educators in engineering, design, building. We're working on wrapping up a book, which has been like giving birth to a small cow. But I think it's really focusing on all the issues that we talked about today, and it's been a really great international transatlantic collaboration, not only for Pekka and Matti and me and our colleague Andy back in my office, but also all of our students from Aalto University and Yale have been involved in this process too. And they'll be presenting tomorrow at the World Circular Economic Forum in their work. So I have learned a lot about this from this lecture, and I've been working on this with you for a while. So I hope you all will take advantage of those materials and forgive us the sins of website operability if it's not working right away, but we're working on that now. So yeah, I guess that was the launch, pre-launch launch.
Sorry about that.
Yeah.
We could go on for ages, but I have bad news. We have to throw you out, but luckily Reetta has good news for you.
We would like to invite everybody outdoors for a little snack, healthy snack, so we can discuss in this sort of more leisurely-like environment outdoors. We don't have a forest in the city, but we would like to guide you through our back door to the backyard. So let's enjoy. You're all welcome.